Well, welcome back, folks. Looks like it's the official time to get started. For the announcements today, we're going to be working through these notes here, section 4.4, and we may get into section 4.6. Also, the bigger announcement is that our third exam is going to be next Wednesday. Any questions at the moment, folks? Okay, well, as far as coverage of the exam goes, like we discussed, it's only going to run through section 3.4 up to section 4.1. So the work in 4.2 won't make it on the third exam. This stuff will be on the final exam instead. Same exact properties for the exam materials you're allowed to bring, a calculator as well as one page of notes with both sides on it. Or excuse me, that was a different class. Let me say that again. For the third exam, it's open calculator but closed notes. So calculators are allowed. But the last page of the exam is this one right here. So when you go to study for the real third exam, it's good to have this open and just ready and available. You'll have differentiation formulas. We need this for definitely on this exam. Properties of logarithms to support any logarithmic differentiation. And this information here coming from section 4.1. Well, I should have that exam written either on Thursday or Friday, hoping for Thursday, sooner is better. And so once that's written, I'll be emailing you to contact the testing center. Well, any questions, folks, about their upcoming exam so far?
I have a
Okay,
question. Sorry.
awesome.
Um, are you gonna do kind of an exam review again on Monday, or should we come in for office hours and do a review there?
We are doing the same review thing on Monday. Yes, thanks for mentioning that.
Okay, thank
So
you.
doing like we said before is on Monday, the 11th. Any questions you folks have, whether it comes from WebAssign, a quiz question, something out of the book, someone from a neighbor, someone from any questions from one of these documents, the sample exams, we'll take a look at them and work them out as a class. So thanks for mentioning that as a reminder, Jamie. Think of this review on the 11th as just our third student-directed review. So it's all going to be based off the questions that you all bring. If we run out of questions, we'll go back to section 4.6. But just like last time, I'm not opposed to taking the entire class time to going over questions if there's that many questions. Well, other questions or comments so far? Okay, well, we're definitely getting pretty far through the weeks. We're currently in week 12. This one's week 13. Then it's week 14. We have a week off, week 15 here. And finally, we're in finals week. So we're just about to finish strong. We just need to get through one more exam and a few more sections. So here's where we left off, section 4.4. Well, we finished this problem. We didn't leave off on it. But I wanted to talk about this problem a little bit more because one of the things you'll see in the notes is show all steps using the second derivative test. You'll see that as well on the new quiz number 8, this one here. It mentions show all steps using the increasing decreasing test. So I felt like it's a good idea to just be very specific. What do we mean by all steps? If we're using the increasing decreasing test and finding local minimums and local maximum values, showing all steps pretty much means, let's go back to 4.1, that we have to go calculate the derivative, solve the derivative where it's set equal to 0, showing steps. Let me move this window a little bit more to the right. And then finally, oh, hang on, where are we? This was just finding a critical number. Sorry, I'm in the wrong section. I want to go to 4.2. There you go. This is more on the lines. So when quiz number 8 says show all steps using the increasing decreasing test, what's expected there is you'll calculate the derivative, set it to 0, solve it. But this is part of the required steps. We have to do the analysis on the real number line for the functions increasing and decreasing to support our conclusions. And these steps are required in a certain sense because of what can happen in anything with maximizing or minimizing. So let me pull up this document here down to this spot. So here's what makes these problems kind of tricky. When this shit says show all steps, sure, we know we have to come up with a function f of x. We know we have to differentiate it, set it to 0 and solve. But right here at the red dot, that's not the last step. It's unfortunate too, when we get a critical number, that critical number in no way says you have an absolute max or an absolute min. We have to show the steps to support it. So we use the second derivative test on this problem, which meant we calculated the second derivative, showed it was positive, and that's the all steps part. So this is really tricky again, because once you get the critical number, a lot of times on quizzes or exams, people stop right at that step and say, we have a local min or a local maximum. But going back to this document, let's maybe put this on this page here. We had a function f of x equals x power 5/3. We differentiated it to get this result, 5/3 of x times x power 2/3. We found 0 is the critical number of this function, but it turns out this function had no maximum or minimum whatsoever. So the critical number is not enough on its own to determine if you have a local min or a local max. Let's take this as a screenshot real quick. It's because of these kinds of problems right here, we always have to do the following. Once the critical number is found, we must next pick. There's now two tests, either the first or second. This is a longer sentence than I thought it'd be. Pick either the first or second derivative test. And work through the steps of that test. So we're kind of making a big deal out of this for our first problem of the day. But again, it's mainly because once we go and take a look at, say, a problem like this one, it's not the worst thing to get a critical number out of this, but the hard part is not the critical number. The hard part is proving you either have an absolute maximum or an absolute minimum. And it could be the case that the problem is just flawed. There is no max or min. We have to show that one really exists. Any questions about those ideas so far, folks? About the extra steps after the critical numbers? Okay, well, let's give this a try. And maybe one last parting thought. This is extra tricky because of WebAssign as well. In WebAssign, they won't know if you did the extra steps or not, and you could plug in a critical number and just move through the problem. But that's dangerous because for the purposes of a real quiz situation, you do have to show those extra steps. And that means when you do it on an exam, this would be content on the final exam, you have to show those steps as well for full credit. So I'll try to always make a big deal out of that on these notes, just so that we're not accidentally missing stuff. So let's get started on example 2. This one looks like it comes from the biological sciences. It says the rate in milligrams per carbon. Well, this is a complicated unit. Milligrams of carbon per cubic meter per hour at which photosynthesis takes place for a species of phytoplankton is modeled by this function right here. So I guess P is going to stand for the photosynthesis taking place. I stands for, it says here, light intensity. And the unit for light intensity, it could be lumens, something standard, but it looks like we're using thousands of foot candles. That's just another unit for light intensity. Because this is light intensity, it also implies I is greater than or equal to 0. When the light intensity is 0 exactly, that's total pitch darkness, but you can't have negative darkness. So that's why it has to be non-negative with this inequality. So at minimum, I is 0, and it can take any other larger value after that. The question of the problem says, for what light intensity will we maximize P? So you can imagine the scenario here. Maybe you're a manager of some kind. You're working in producing this. This is the rate of photosynthesis taking place. And your goal is to maximize that outcome. So you need to know when to turn the lights on. You can't have the lights set to 0. If I hit 0, nothing happens. You don't have any photosynthesis taking place. But if I is set, the light intensity I is set too high, you're going to kill the phytoplankton. And now again, there's no actual photosynthesis. So somewhere there's got to be a sweet spot. And using calculus, we can find it. If this is a fairly accurate model, then we should get very great results. So first thing you've got to do is differentiate this function and pick a test. Probably we're using the first derivative test as it's indicated up here, but that's because as you look at this function, let's make a really quick comment. The second derivative is difficult to calculate. The reason for that is just the first derivative alone is a quotient, or excuse me, yes, a quotient rule. Second derivative is an even harder quotient rule. So it could take a couple pages just to get to the second derivative. And it gets even worse. Once you get to your second derivative, it's probably going to be a complicated looking function. And to use the second derivative test like we did on the last problem, you have to show that the second derivative is either always positive or always negative. That's not always easy to show. It worked out on example 1 pretty well because the second derivative came out as just a constant, as simple as possible, always positive. But in our current problem, it's not going to be a simple constant like that. It looks like the second derivative test is just a total nightmare. So if you notice the derivative looks hard, this suggests use first derivative test. So that's what we'll do on this one. And that's kind of what you would probably guess because it's just sort of sitting right here, first derivative test. Like we did with the second derivative test, this one has a small tweak given in. This one is tuned for absolute extreme values. To make that happen, we have to have this inequality hold for all x less than c. And we have to have this inequality, the derivative negative, for all x bigger than c. That will give us an absolute maximum. And if we can show the reverse is true, we'll have an absolute minimum. But essentially showing any of this work through the first derivative test is just doing this stuff all over again. Or hang on, 4.2, this stuff all over again. We're going down to a number line and just resolving where's the derivative positive, where is it negative, for example. Well, I think we're ready to start this off in earnest. This is a function p. Think of p as the y variable, and the variable x is I in this problem. So let's launch into the first derivative, dp di. And you know what, let's maybe back off just a bit. Just because this is an easy one to miss steps on during a quiz setting and an exam setting, and even on WebAssign, let's write out the steps very carefully. Step 1 is to do the following. We're finding a critical number, so we calculate the derivative of P, photosynthesis, with respect to I, the light intensity. So differentiating this is now a quotient rule problem. Setup should go about like this. Let's still use that same color coding. It's not that this is a hard derivative, but it's just more abstract because we don't have x's and y's. So setup should look like this. 100i prime, so we're differentiating the numerator, multiplied by I squared plus I plus 4, subtract 100i, multiply it by I squared plus I plus 4, prime on there, just to not forget that we have to differentiate that one. And that fraction bar got longer than I would have expected. Denominator is I squared plus I plus 4 to the second power. So that's our first derivative. Now we're just running through the quotient rule. As we do that, these are still kind of tricky derivatives. Any volunteer to say what this one would come out as, highlighted in yellow? What would be the derivative of 100i? Good call, Jamie. This one is just 100. Think of this as like taking the derivative of 100 times x. You would just get the constant 100 because x is to power 1. Same on this. Again, think of your I as the x. I is to power 1, so just 100. So let's write that down next on the new line. So dp di is now equal to, that should be long enough, I hope, 100 for where we took the derivative of 100i. It's multiplying the group, I squared plus I plus 4. We'll distribute that on the next step. Then over here, copy negative 100i. And new derivative. We need to handle what should happen with this one. Anyone else have a good answer for what this derivative should come out as? Eli says 2i plus 1. Good call. That's exactly what this one should resolve down to. So notice this was actually pretty tricky kind of stuff when we first looked at these kinds of derivatives in section 3.2. But the more and more we get just fluent with these kinds of properties with differentiation, it's not as bad. It just takes a little bit of studying the problem carefully, determining what's playing the role of x. So just like you said, 2i plus 1. I is kind of a funky variable. Try to make your i's not look like the number 1 and you should be in good shape. Denominator, after we clear this highlighting, the denominator is pretty much just staying exactly where it is the whole time. I squared plus I plus 4. Sometimes people FOIL out this denominator, but it's of no value. It's only going to get eliminated when we go to get the critical number either way. So let me keep on scrolling down. We've got our first derivative. At this stage, it's a great as it stands, but we want to simplify this as much as feasibly possible. So on the next step, dp di comes out this way. By the red dot, distribute 100 inside. We've now got 100i squared plus 100i plus 400 and distribute again over here. This will turn into negative 200 I squared minus 100 I. So that's our entire numerator so far. Copying down denominator, I squared plus I plus 4 power 2. This gives us a couple quick cancellations. We can now eliminate negative 100i, so those are gone. Got a cancellation, but these are like terms here and here. So the next step, we've got 100i squared. Or hang on, forgot to combine those. Let me start with just the constant 400. Then where these brackets were, that was supposed to help me. 100i squared minus 200i squared is negative 100i squared. Divide by I squared plus I plus 4. Numerator is pretty simplified, but we also need to factor that thing. So let's factor out 100 is a good start, I'd say. 100 leaves behind 4 minus I squared, all of which is divided by I squared plus I plus 4 to the second power. Eli says, why is the squared in the negative 200i squared a negative 100i squared? Oh, it's because of this right here combined as like terms, just leaving us with the negative 100 out. Oh, glad to hear that, but I'm glad you asked the question as well. You never know how many people have the same exact question. Other questions at the moment? Trying to take that highlighting off. That's amazing how tricky that is, actually. There we go. Okay, so now down to this step, it's looking more simplified, but where the red dot is, one last thing we can do is just factor. So we have 100, 4 minus I squared can be factored down to 2 plus I, multiplying 2 minus I, still divide by I squared, plus I, plus 4. I notice my penmanship goes bad in the denominator because it's honestly kind of tedious just to copy that down each and every time. But now that we've done it, we have dpdi right here in its most simplified form. Well, simplified for our purposes, getting a critical number. We're still in step 1, finding a critical number, but we solved step 1 the moment we solve this equation right here. We're setting everything to the left equal to 0, but the only way this equation could ever come out as true is if we put a -2 right here where the red dot is. So that's our first solution. I equals -2. Or if we put over here, +2, I equals 2, that's the second solution. We don't get anything from the denominator. In fact, if you wanted to, you could take a step of just multiplying both sides by it. You're feeding it off to 0, killing it. So it's only about the numerator that's going to allow us to get a 0. But there's more to this story. There's actually only one critical number. If you feel like the negative is suspicious, then you're on the right track. You have to remember I is the light intensity in the problem, which means there's no actual meaning for negative light intensity in this situation. In other words, I is a positive quantity. So we eliminate this one. Let's just put down a quick explanation. I is greater than or equal to 0 in this problem. So that one right here is our critical number. I equals 2 is the critical number. All right, crit for critical, hash for number of P, where P is this function up here, rate of photosynthesis. We did it, folks. That's the step 1. The question is asking for what light intensity is P a maximum, and it's so tempting to just stop right here and say 2. But then we've missed a lot of steps and potentially a lot of credit on a real quiz or a real exam. We have to now pick a test to prove that that 2 as a critical number really is a maximum or a minimum, because once again, it could be this situation where we found a critical number, x equals 0 on this, but at 0 being a critical number didn't give us anything at all, no minimums, no maximums. So the purpose of step 2 is like a reality check. We're going to show that there really is, let's see here, a maximum of the problem. You might have wondered why not a minimum, but we'll show once and for all there really is a max, and it happens at I equals 2. Let's see if we can do it in this space here. That should fit, I think. Here is step 2. In step 2, we use these values. Looks like this value is how I should say it. I equals 2 is the critical number. So now we go next to a number line. It would be an x-axis in a generic problem, but for this problem, it's a I-axis. I for light intensity. We have an intensity of 2 here, value of 0 where the domain starts. And so now we have to test 2 regions, this finitely long one and this infinitely long one going off to infinity. The thing we're testing is that object, the derivative. So we put dp di here, dp di here as well, and now we're testing the signs. So this is what the setup is always going to look like for step 2 whenever we're using the first derivative test. Doesn't matter if it's section 4.1 and quiz number 8. We're doing that on quiz number 8, by the way. And it doesn't matter if we're in section 4.4 doing this right here. So in this region, the easiest value to pick would be a 1. So let's just do a really fast computation. What is the derivative of P with respect to I? Evaluated at I equals 1. Here's the derivative, and if you follow all these inequalities, it takes us down to this. We can plug it in right here, or it could be just as easier to plug it into this one. There's less stuff. Totally up to you. I'll go with this right here. Plug 1 here and you get 100. 3 times 1, the denominator is going to be at 1 plus 4, so 6 squared for 36. And all we need to know is what is the sign of that thing? It comes out positive, so over here, we'll say greater than 0. And in this region from 0 to 2, what this all tells us is that the function p for photosynthesis is increasing. It's increasing only because the derivative is positive. So that was fun. We'll do it one more time over here. Our hope of hopes is that we have less than 0. If it comes out greater than 0, we have a huge problem. Any questions to this stage? Okay, let's pick another test value. You don't have to work hard, so you could pick a 2.1, but that's kind of an awkward value to work with. I think 3 is the easiest value to throw in there. So pick the most convenient value possible, take this and drop it into your derivative. Here it is by the red dot. So now this time dp di, evaluation at light intensity I, set to 3 this time, gives us 100, a 5, a -1. In the denominator, well, whatever it comes out as, it's positive because of this power 2 right there. So let's just quickly write in, we're throwing a 3, so it's 9, plus 3, plus 4, squared. And all we want to know is what is the sign? Because of that one factor that's negative, the whole thing is negative as well. Back up here, that means rate of photosynthesis, dPdI, also negative. And now the conclusion down below, let me just fix some of this color coding first. There we go. Conclusion down below is now that P is decreasing. And same idea, this is all from section 4.2. If the derivative is negative on a region, the function has to decrease. So photosynthesis started increasing when the light is between 0 and 2, but something happens. Right at 2, photosynthesis starts to transition to no longer increasing, it starts to decrease. In other words, the lights are on too high beyond 2, we're just cooking all the phytoplankton. Looks like 2 exactly, in other words, 2,000 foot candles, interesting unit, is the optimal value for photosynthesis. So this is step 3. All we're doing here is giving a conclusion. Any questions or comments, folks, right before we give our conclusion in step 3? Okay, before we go to give the conclusion, we actually need to be a little bit careful on this. I equals 2 is a critical number. From this chart here, it's the critical number that leads to an absolute maximum, but it was asking for us to give the light intensity. So the answer to this question is not the amount of photosynthesis you're going to get at that's maximized. It's the value you should turn the lights on to, I itself, that answers the question. So we'll say down below here, through the first derivative test, I equals 2 maximizes P by the first derivative test. Again, what the first derivative test says, if you have an absolute maximum, then there's some critical number C. Our critical number was 2, for which the first derivative, f prime, was positive for all x less than C. And that's what's happening at 2, that's our critical number C, and the first derivative is positive for all values less than C. Then if you can turn it around and show that f prime is negative for all x less than your critical number C, and our problem again, C is 2. Let's take a look. We went to the right of C, derivative is negative, then the foregone conclusion is you have an absolute maximum in your problem. If the estimates went a different way, we'd have said absolute minimum instead. Let's leave that chart there on the notes just for quicker reference on how we got to that last conclusion. And honestly, I think for a lot of people, when you go to write down this sign chart in step 2, you might not even look at the first derivative test again because it's kind of saying already what the conclusion is. The function went from increasing to decreasing across 2. So if we did a really simple sketch, that's what the function looks like around 2 at absolute maximum value. What we did, folks, this is running through the first derivative test in completion. The thing that's easy to miss is this right here. Let's make another big comment. Don't forget this step. Let's see, it's worth a lot. Well, it would depend on the problem, but if we're saying like a 10-point question on an exam setting, it could be as much as 4 points potentially. Well, any last questions, folks? Finishing off that second example there. Okay, I think we're ready then to move on to the next one. We only have 2 more examples to get through on these notes. And this is the next one. At this stage, it's totally up to us to decide what test we want to use. There's no exact hints. And this is how it would be on a real quiz or exam problem. It's really just up to you which test you decide to use. So we want to analyze the function, see if it's easy to calculate the second derivative. If that's the case, second derivative test is a good shot. But for this problem right here, it looks like the first thing we have to do is actually build the function. Then we can pick the right test. So example 3 is actually very, very similar to example 1. Example 1 never supplied the original function. We had to do a little bit of analysis and come up with that function f of x down here. So think of example 3 as really just an example 1 taking to an extreme. So here's the setup. It says we have a rectangular storage container with an open top, so no lid on it. It's to have a total volume of 10 cubic meters. It seems like a lot of volume. Maybe we're doing a freezer, who knows? And other information is the length of the base is twice the width. From all that so far, I think the best problem solving strategy is actually just draw a picture to organize all of this information. I'm not very good at this, so let me give this a good try. We want the length of the base. The length of the base is twice the width. So I would try to maybe make it go like this. Actually practiced this before class today, so let's hope that practice paid off. Doesn't seem like it is. Hang on. I tried to control Z at one step, and control Z on these notes is weird. It erases in random order. Let me make sure I didn't do anything up here. Okay. So second attempt on the box. Strategy is to write 2 rectangles down and then just hope you can connect the line segments. So I have a line segment going this way, this way, and for this one, it's hidden till it gets to this edge, and then it's revealed. So we're looking in with the open top. We have a length. The length is the larger one, so I'll call this the length. We have a width and a height. So here's our diagram so far to help us out. Using this statement, the length of the base is twice the width. It's a good call to give a variable, say, x for w. Then the length is twice that, so 2x. There's no information to tie that in together with the height, unfortunately. So the height needs a whole new variable. Let's give it variable y. So there it is. That's our setup so far. We also have information about volume. It's 10 cubic meters in this problem. But the formula for volume, it's just the product of all the dimensions, the width, the length, times the height. So in place of volume, we can now put in the width x, the length 2x, and the height y. That's equal to 10 cubic meters. I'll drop the unit and just call it 10. So our more cleaned up equation is now 2x squared y equals 10. So far, this is how much I've gone through the problem. Just that part. We drew a box. We used the information of how the width and the length are related. And then we just used the fact that the volume is 10 cubic meters to come down to that equation there. Any questions at the moment, folks, with this step? Okay, I guess the next thing to start focusing on is we're trying to find the cost of materials for the cheapest such container. The container, they'll have 10 cubic meters and this relationship with the length and the width. So now we need to go through the material costs. Jamie said, where did the extra X come from? I think you're referring to this X potential. Oh, didn't mean to scribble on it. Let me try again. Are you referring to this X right here? Gotcha. So where that came from is the formula volume equals length times width times height. And kind of mixed up the letters, but in multiplication, you can change these letters in either direction you like. The width here was X, and so we just plugged X into that location. The length is here, and that's 2X, so we plugged 2X there. And the height was Y. Does that make sense there on where this extraneous X came from? Yes, absolutely. Other questions so far? Okay, well, let's go off to this next step right here. It says materials for the base cost $10 per square meter. So let's maybe say about right here, base cost. If it's $10 per square meter, we'll find out the cost of the base. By base, we're referring to this part of the box by saying its area multiplied by $6. Put in maybe the unit first. It's the area times $6 per cubic meter. But the area is not too bad to come up with. It's going to be just, let me erase some of these highlightings temporarily. So if we want the area of the base here, we'll just take the width times the length. So it's going to be equal to X times 2X multiplied by the $6 per, oh, I put cubic meter there. That's area, square meter. So the meter squares will cancel off and we'll just have this times a 6. Oh dear, thanks for spotting that. Material sides for the sides is $6, but for the base, it's $10 per square meter. Good eye, Eli. Thanks for spotting that right there. Should have left that highlighted if that was meant to be my guide like that. So let me put in here the correction. The base cost, it's more expensive. I guess that's to support the weight of whatever's going in this thing. We don't ask questions. We're just going to minimize its cost. So times $10 per square meter. So there should be a 10 down there as well. Again, thanks for spotting that one. So finally, we can say altogether, the cost of the base is 2x squared times 10. That means it's altogether 20x squared in dollars. So we'll find the cost of the base by picking a value for X and just throwing it inside right here. And by the way, now that we're saying that, notice there is an actual domain condition on X. X can't be 0, for example, because we don't have a box if X is 0. X can't be negative. That would make no sense whatsoever. So in this problem, X, let's say it may be up here. X is a positive quantity. It's a little bit different than the light intensity situation because in light intensity, we said I is greater than or equal to 0. So 0 was a valid value for light intensity in this problem, but 0 is not a valid value for X whatsoever because once again, If x is 0, we don't have a width or a length. We have nothing essentially. Well, we've got the material cost for the base. Now we have to do it all over again and do the same thing for this. Material cost for the sides is $6 per square meter. So let's say here, sides cost it'll be the area multiplied by this time, $6 per square meter. A little bit cheap, I guess. Whatever's happening on this box, we're more concerned about the weight on the bottom than on the sides. Well, if we're getting the area, let me redo the highlighting on this box. This one's a little bit trickier because there's two kinds of areas we can come up with. There is these two faces, the front and the back. So let's start with those two. This is going to be equal to the area of the front face is going to be the length x times the height, which is y. Let's throw down a y here for easier reference. So it's going to be x times y, but that's the front face and the back face, so we have to double it. So 2 copies of xy takes care of these two sides right here. Now we have to turn it all around and get the left side and the right side. So let me undo this highlighting. Next thing we're putting in is the area of the side to the right, highlighted there. The area of the side to the left, highlighted this way. There'll be plus, just like the front and the back face, there's 2 faces with the same exact area, the left and the right. So we put a times 2 there. And now that we're looking at the area of this side of the face, it's just going to be 2x times y. So times 2xy, close that parenthesis, the whole thing is being multiplied by 6. So that's our expression, and it really isn't simple coming up with that. Really, the only thing that allows me to get the right thing in, with a little bit of help of the class getting the right dollar cost, is this drawing right here. Without this, I think I would take forever to come up with the right values, and I wouldn't even be sure if I got the right stuff. But seeing is believing. If you can tie it together with a diagram, it really helps a lot. Any questions at all, folks, coming up with this expression? Okay, let me just see if I can carefully reset the highlighting here. There we go. Let's continue to simplify this just to see what we get. So inside the parenthesis, we have 2xy plus 4xy, so it's 6xy altogether, multiplied by 6. So the side's total cost is 36xy. Now, the base cost is great. It's just 20x squared. The thing that's great about it is it involves only one variable, x and x alone. This one's awkward because it involves 2 variables, and we have no idea how to optimize if there's more than one variable. That would involve calculus 3 methods. So what we do is we come over here. We gave this equation a name. This is called the constraint equation. And constraint is a good name here. When we said it had to have 10 cubic meters of volume, that's a massive constraint on what can happen in this problem. And it constrains what y itself can be. We can just divide by 2x squared and solve for y. We'll get, let's see here, we should probably start highlighting these a little bit more. Let's go with purple. So we have a 36xy. Over here, let's hide that test. Y is going to be equal to 10 divided by 2x squared. So this would be 5 to the power, or excuse me, 5 times x to the power negative 2. Okay, so we're minimizing the cost of this box. We're not asking what the box is used for. Working through the constraint, we have a new value for y, and we can say over here, the sides cost is now equal to 36x multiplied by the value for y, 5x powered negative 2, And so altogether, this comes out as 36 by 5. I think that's 180 x to the power of -1. Let me double check. I've got, okay, just in case we need a calculator, these numbers are getting a little bit wild. So we are not even on step 1 yet, but here's what we've got. We're trying to minimize the cost of this box. Let's double check. Find the cost of materials for the cheapest such container. So we now can build the new function. The total cost function is take this cost right here for the base, this cost right here for the sides, and write out f of x equals 20x squared plus 180 x power -1. So now we're in business, folks. We have a function, and that's the function that we're trying to optimize in this problem. Just as a reminder, it does come with a further domain condition. X has to be strictly positive on this one, not even 0 this time. But if it was 0, notice the cost through this function would be $0. So in kind of a way, it makes sense. But we're about to minimize the cost function here. Any questions at all, folks, before we go through those steps? Okay, so here's finally step 1. We have a function f. We need its critical number. Let's come down here, just write this out. Step 1. And maybe before we get too far ahead, let's look at this function really closely. The first derivative is super fast, and so is the second derivative. If that's the case, this is a really great situation for using the second derivative test. So let's say that here. Using second derivative test. And this really becomes easier to pick because you'll notice that second derivative test is a really bad failure on anything like this one right here. Notice how much steps it took just to get to the first derivative. So these become really easy tests to pick down the line. So on that second derivative test, step 1 is still calculate f prime of x. So here's the function for f prime will be 40x minus 180 x power -2. Once we get the derivative, the very next thing we do is we set it equal to 0 and we solve to get a critical number out. So now we're focusing on this part, this equation here. Let's add 180 x power -2 to both sides. We get 40x equals 180, and x power -2 could be rewritten this way, x squared in the denominator. You don't have to do that, but if it's helpful for visualization on the next step, not a bad step to take. So what we'll do next is multiply the right-hand side by x squared, multiply the left-hand side by x squared, and our new equation is that 40x cubed is 180. We now need to divide 180 by 40. Let's see what that is. A nice even 4.5, so x cubed is 4.5. And last step to take here, cube root both sides, and we get x equals, let's maybe write it this way. Oh dear. It's a weird habit to realize that you can't use Control-Z on these notes, or the digital ink kind of randomly deletes. Let me know if you read notes and just something is missing. I might have accidentally Control-Z something, and I'll be happy to go back to those notes and find the mistake and correct it if that ever happens. So here x equals the cube root of 4.5. And just to emphasize what we found, we'll say is the critical number of f. Looks like we're getting kind of in a habit of using this highlighting once we find a critical number. And now we're ready to go off to the second step. Well, again, it's always good to remind ourselves This is not the full process. It's super tricky in WebAssign because WebAssign won't know if you complete the next steps or not if you give them that answer. But step 2 has to be shown on quizzes and exams. Let's emphasize this right here because it's just easy to miss this step. We must show this for full credit. So I encourage you to do the same on WebAssign. That way you're getting that practice and not suddenly having to relearn a bunch of stuff when you go to do this as an exam situation. Try to do the problems, in other words, like you're expecting to do them on a real exam, and that'll help out a tremendous amount. So what is step 2? Well, for using the second derivative test, it's just to calculate the second derivative. So here's where f prime is by the red dot. Now up to the second derivative, f double prime of x, we're going to get 40 plus 360 x to the power -3. So that's our second derivative finally. Let me double check. 2 came down here, so that's why it's positive 360. New power is now -3. That function's kind of suspicious, however. Let's take just a quick look at it in the graphing calculator. 40 plus 360, x power -3. So this function is either sometimes negative down here, sometimes positive way up here. Actually, this is really bad for us if we're using the second derivative test. Here's why. In the second derivative test, we need to show that the second derivative is either always positive, like here in green, then we have an absolute minimum. That's what we're trying to find. We're minimizing cost. Or if we're trying to maximize something, we need to show that the second derivative is always negative, but for all x's, and then we have a maximum. So in our problem, if we're looking for a minimum, and we see this graph, that's a concern. There are some x's for which it's negative, and some x's for which it's positive. But there is a resolution to this. Anyone see why the second derivative test still works, even though this function here is sometimes positive and sometimes negative? It's definitely kind of tricky if you're not too sure. So with the way it looks, reading out the second derivative test verbatim, it looks like we have a massive failure here. We couldn't have used the second derivative test because we want that to be positive for all x's, it says, but we're looking at a graph where it goes negative. But here's the resolution to this conundrum that we're facing. Recall that when we went to set up our function, we had a condition. It's all about the context. X is the length of the width of a box in this problem. That means x could never be negative. So if we put in that domain condition here, we'd go 0 is less x. And this is the function we're really looking at. It's a function that's always positive no matter what. Looks like it has a horizontal asymptote at height 40. So that tells us over here, we can say it is greater than or equal to 0 for all x positive. We can say this part because that's the only valid values of x in this problem, x larger than 0. And if we have greater than or equal to 0 here, let's pull up that test. Oh, we didn't mean to delete the test. There we go. We have an absolute minimum. So step 3 is now in effect, where we can write down our conclusion. Any questions, folks, with step 2?
So if it asked like for do we only have to do this in when it's a negative exponent, or do we have to do this when it would also like be a positive exponent?
We would have to do it for all values, yeah. No matter what the second derivative comes out as, we have to show this is true, that the second derivative is always positive for the for the valid values of x in your problem, x bigger than 0. Would have said for all x in the domain of f, that's what we're referring to right here. But yeah, no matter how this problem comes out as, if this is positive or negative, if it's a fraction, if it's even more complicated, you still have to show this right here by the red dot. This is what makes the second derivative test sometimes just a terrible option. But if your second derivative comes out not too bad, like a constant in example 1, or like this one in example 3, then it's a good test to use. Other questions about that so far?
Thank you.
Yeah, absolutely. Thanks for asking about that. Okay, well, to finish off this problem, we have to remind ourselves, what were we going for? Like in example 2, the answer was the light intensity, not the function p of that light intensity. So here, the answer could be the width of the box, cube root of 4.5, or it could be the minimum cost. We have to double check. So up here it says, find the cost of the materials for the cheapest such container. That means in this problem, we need to take the critical number, cube root 4.5, and plug it inside our original function f. It's nowhere even in sight. That's the second derivative. That's the first derivative. There it is. That's our original function f. We need a screenshot of that one as well, looks like. I'll delete that in a moment, but just for easy reference, we can now say the cost, let's say this slightly better, the minimum cost of materials is f at, take your critical number, it's 4.5 cube rooted, plug it inside the original function f, and we have 20 something squared plus 180 something to the power of -1. In both boxes, we're putting in the critical number, cube root 4.5, cube root 4.5, and this is the calculator part of the problem. Whatever the answer comes out as, it's going to be a cost, so we'll naturally round this to the nearest cent. So back to Desmos. Here's our last step with this one. Take 20 times 4.5, power 1/3 is a great way to put in the cube root. This whole thing is raised to power 2. You know, it might be better to just type this in as times 4.5 to the power of, if it's power 2 with a cube root, I think it's easier to just type in a power 2/3 altogether, just to make sure it's coming out right. Then plus 180 times 4.5 to the power, this is -1 divided by 3 as an exponent. So -1/3. Finally, this is our cost. It's a more expensive box than I would have thought, $163.54. And we did it, folks. That's the minimum cost in this problem. If we were doing this in real life, you'd probably want to round that up to like 165, since things always cost a little bit more than you'd anticipate. But as for an exact mathematical value, it'd come out to that place. What about the cube root? Are you referring to the cube root 4.5 here? Yeah, I typed it in a kind of a strange way. What I did was, this is the cube root of 4.5 to the second power, so I wrote it in as 2/3. I was typing it in Desmos, and it seemed like it was just formatting weird. But if we wrote it in verbatim like this, it might come out as 20. Let's say 4.5 power 1/3, then another parenthesis to power 2. It just looks like it's formatted weird. That's supposed to be an exponent. Almost looks like it's not. But the power 2 times the power 1/3 is the power 2/3 up here. So that's plus 180. 4.5, we got these double parentheses, 4.5 power 1/3. So that took care of the cube root right here. Then the whole thing is to power -1. So same value either way. This is if you want to emphasize the cube root getting squared. I think this is easier to type in that way. That's why I went to that route. Other questions about that or other questions so far? Okay, well, it looks like we're down to just one last question on this set. And we've got about 15 minutes. I think we might be able to get through this last one. So let's give this last one a try. This one is from a science called pharmacokinetics, a whole discipline of seeing what happens in your bloodstream with the drug concentration after you either inject something or take an oral medication and so on. So people going on to pharmacy school know all about these kinds of functions like this one right here. So the setup on this one says, blood alcohol level, milligrams per liter of blood, T minutes after consumption of a hard liquor is given by something called a surge function. It's this function right here. So B to say blood alcohol, T is going to be time after the shot was taken. And just to visualize what we're looking at here, let's plot that surge function. So B of T equals first 26.9 T e to the power -0.1095 T. There's a domain of condition on this T. This time, it just has to be greater than or equal to 0. 0 is valid here because at time 0, that's the instant right before the shot went down your throat or something like that. But take a look at that function. It's called a surge function because this is what happens with a lot of drug concentrations. Very rapidly, it hits some maximum value, but then slowly over time, it kind of tapers off. For some medications, they work really hard to try to show if you redose, a certain level, like maybe 50, is always maintained. But in the case of hard liquor, this is good. You want it to kind of leave your system right away, essentially. And that's the function we're looking at. The question, though, is at what time? So we're not going to find the blood alcohol concentration. We just want the input variable T for time. Is the blood alcohol level at its peak? Looking here, well, we would say maybe 9.13242, but we have to know how to do this without using a graph, which is reasonable because our functions sometimes get really complicated. For example, it's possible to have functions with more than one constant, like say a constant A, a constant C that have different meanings. And we can't just plot those functions immediately. So think of this problem as something that is not the worst case for how complicated it is to do by paper, but it's a decent problem where you're given a function right away. It makes an excellent exam question. So we're not taking all this additional time just setting up a function like we did here. So here's how it starts. Now, looking at that function, differentiating it once is already the product rule. Because of that, this is a good candidate for first derivative test. So we'll apply that test on this one. To start out here, step 1. We're just going to differentiate the function outright. It is a product rule, so let's do this one carefully, like we did with the quotient rule earlier. For the first factor, I'll take together 26.9 T. For the second factor in the product rule, let's put together the exponential. Looking at that a little bit closer, this is product rule together with chain rule. So maybe it's a good idea we're taking this carefully. So now we're at the derivative, B prime at T. It's going to be 26.9 T prime, multiplying e to the power -0.1095 T. Sounds like a tax form. Then in product rule, we go plus 26.9 T. And now we're differentiating this function, e to the power -1095 T. So we've done the setup of the product rule to this step. Now, just for ease of the next steps, let's take a look at what the chain rule will look like over here. Oh, I made a mistake. Don't forget to put your primes on these, just as a reminder, you're differentiating in those spots. Well, after the product rule, this one's not a hard derivative, it's just 26.9. But that one is, so let's again take a careful look at it. This part right here is the inner function. The base e exponential is the outer function. So now we're ready for our next step. B prime of t equals, I'll keep the color coding where the derivative was and just black when we're copying. This is going to be at 26.9 here. It'll multiply that exponential, e power negative 1095t, then add 26.9t. And now we're multiplying by this derivative here. Working this out carefully because they're always tricky. The first thing you do is take the derivative of the base e exponential. It goes just like that. Whatever is inside those parentheses, we'll dump it in there. And the chain rule says, multiply by the derivative of what goes inside. What goes inside is 2, the inner function, so that's why we have an extra prime right here. And now we copy in that inner function twice. Negative 0.1095 t here, negative 0.1095 t there. Okay, so this is the result of the chain rule. One last derivative to go, and we'll have our b prime of t function. I feel like we should pause at this step though. Any questions at the moment with where we're at? Okay, well, let's keep on going. Here, when we take this derivative, it's just a negative 0.1095, which will multiply the 26.9. So our next step is that b prime of t, 26.9, e power negative 1095, t plus 26.9t it's being multiplied by this constant, negative 0.1095. That's the value we get after differentiating. And all that's left over is that exponential once more. E to the power, negative 0.1095 t. So we still have to multiply these two numbers together. But also notice we have the same exponential on both terms. We might as well just factor it out to make life easier. So our last step is e to the negative 0.1095 t. Factor that out, leaves behind this 26.9. And these two numbers, this is a good time to multiply them together. So 26.9 times negative 0.1095, we get a negative 2.94555. So negative 2.54. Oh, I think I already forgot. So let me double check. 94555. I knew that didn't feel right. 94555. There's still a variable t from right here. And I think we got it, folks. This is our derivative. And finally, its most simplified form. Any questions at the moment getting to that step? Okay, well, still in step one, we take this whole thing, set it equal to 0 and solve. We don't get anything from this right here. The base e exponential never obtains a 0 value, like we mentioned earlier. So the only way you could get this equation to come out as 0 is if the second factor right here is the culprit. So this will imply 26.9 minus 2.94555t is 0. So we'll do two steps. We're going to subtract 26.9, divide by the factor negative 2.94555. And here's our result. So first subtract 26.9 from both sides. You have a negative 26.9. Then we're dividing by negative 2.945555. And we get this. This is in time, but time was measured in minutes, not hours, so that's good. It says we have a critical number right at around 9.13 minutes. So T equals 9.13 minutes is the critical number of B, because the function is B. I almost wanted to say of F. But we're not done. We found the critical number, but now we have to execute all the remaining steps of the first derivative test. Really, it's not too bad, but it takes some time to write these all out. I think I might have misestimated the amount of time it might have taken to complete this one. We're now in step 2. And looking at the clock, I've got 4 minutes to rush through this. That's probably not fair to everyone in this class. So I think a better option is we'll come back to this one next Monday if we have time after a review before the exam. And if we have to, we'll come back to this after the exam to finish it off. I'd hate to rush through this problem when the first derivative test steps are a little bit tricky always. Well, this will be our stopping point then, folks. And just a reminder, when we come back next week on the 13th, we're going to have our third exam. So that means on the 11th, next Monday, we'll be doing our third informal review day. So come armed with questions you'd like to talk about, and we'll have a great time reviewing. Any last questions or comments or parting words before we call it a day? Okay, well, have a great afternoon, folks. I'll talk to you all later then. Thanks, Eddie.